Welcome back, folks. We're going to look at a very particular type of signal that is incredibly useful to us. Okay, everything that we do can be broken into this type of signal. So we got to find a good way to work with them. And we're going to work with them by using complex numbers to represent them. So if you've been keeping up and you're comfortable with complex numbers after the last series of videos, now we're going to put them to use, and we're going to put them to use representing sinusoidal signals. So that's voltages and currents that are represented as cosine functions or sine functions. So we group those together because they're all sinusoidal. Okay, before we do that, let's take a look at how we define a sine or a cosine, a sinusoidal signal. Okay, so I have a couple of them plotted here. And we can start to look at the blue one. And each of these is defined by three values. Okay, and there's a couple different ways that we can talk about a few of those values. So, but they're all grouped into these three groups of parameters. So let's look at the first one. So all of these have some vertical size, they have some horizontal size, and then they can be moved left to right as well. If we move it up and down, we have another number for that, but it's not really part of the sinusoid. Okay, so let's see if we want to talk about this. Let's say we're going to have a sinusoid, and we want to talk about the vertical stretch, the vertical size. Okay, we want to talk about the horizontal size. And we can also talk about the horizontal shift. Okay, if we slide it back and forth, left and right, shift. Let's try to make that legible. I have high standards, clearly. Okay. Horizontal shift, the horizontal size, I guess I should have written size there, vertical size as well. Okay, so the vertical size, we're talking about the distance. Let's focus on the blue one here. We're talking about the distance from here to here. Excuse me. Okay, this distance here. And if we measure that distance, we can do it in three different ways. Okay, and we can describe that as a peak voltage. We can describe it as what we call a peak-to-peak voltage. Okay, and then in some instances we have a special way to describe it called the root mean square, or RMS voltage. Okay, I'm going to leave that one to another video, but I want you to be aware that it's there. When we start representing these as complex numbers, the one we're really interested in is this peak voltage. Okay, so it's not the most important, but as we represent these as complex numbers, that's what we're going to be dealing with. So the way I've drawn this up here, this is our peak-to-peak voltage. Okay, so you might see that as V and then a subscript of PP for peak-to-peak. If I wanted to measure just the peak, we really just take half of that. Okay, so same peak up here, and then since we have no shift up or down in this particular waveform, we can say this one here is the peak value. Okay, and if it's a sinusoid, those are easily related. We can just say that the voltage peak is equal to the voltage peak to peak divided by 2. And it's that simple. Okay, measuring peak to peak is easier on an oscilloscope, because I can just go from here to here, and I can make that measurement much easier than trying to figure out where the zero is. Okay, so that's one reason we might use peak to peak over peak. But there are just two ways to talk about how tall the waveform is. Okay, RMS, like I said, I'm going to leave that to another video. That's a whole nother topic. It has to do with how much power is dissipated when the signal's put across a circuit, if it's a voltage. And I did call this one a voltage. Look at that. Could be a current too. All right, so that's the vertical size. The horizontal size, okay, we can take this whole thing and we can kind of like squish it like an accordion or stretch it out. And that all has to do with how many times it repeats itself over a period of time. Okay, so for that one, we can describe that in a number of ways. We can talk about the period. Okay, this is how long it takes to repeat itself. So we measure it as a period of time. Okay, and we call that one capital T. We can take that and we can turn it into a frequency. Okay, and we can talk about the frequency in terms of how many times it repeats itself in 1 second. Okay, so similar information, just in a different format. Okay, we call that F. Okay, and then we have this other way to talk about it, and it's going to make more sense as we get deeper into this series of videos, but we talk about the angular frequency. Okay, that's in a slightly different unit. Angular frequency, that one's going to be in radians per second. Okay, oops, I wasn't writing units there. Well, that's what it is. It is in radians per second. But angular frequency, we're going to use the Greek letter omega. Looks like a little lowercase w, but it's an omega. Don't call it don't call it a w. Okay, so again, when we're dealing with representing these sines and cosines as complex numbers, we're mostly going to be interested in this one. Okay, this angular frequency. All right, the horizontal shift, one of these is used much more than the others, but we can talk about I think the one that's not commonly used, we can talk about it as just how much time is it shifted over, right? Our horizontal axis is time. In this case, it's in milliseconds. So we can say, well, how far is it shifted in milliseconds? But that one's really not common. You don't see that. More often than not, we talk about phase shift. Okay, and we talk about that in terms of degrees. We call that theta. Okay, so it's like an O with a horizontal line across it. That's our variable for that one. Okay, and that one's going to be much more common. And since it's we talk about it in terms of an angle, it can be either in degrees or in radians. Okay, so all of these things, it's behind my head, all of these things help us describe some aspect of these cosines, okay, or sines. Could be either, really. And we put them all together. Okay, each of these, the blue and the red waveform at the top there, let me scroll down and get a little room here, can be described in general form. Since I made them voltages, I'll use a lowercase v, and it's a function of time, so it's a lowercase to indicate that it is time variant. Okay, and we can say, well, it's got some amplitude, and that's going to be in volts in this case, and it's a cosine, and inside that cosine there's a frequency, omega, and we multiply that by t, right, because this whole thing has to be a function of t, that we see there. And then to shift it, we add an angle, plus theta, like that. Okay, since it's a voltage, it should get a unit, right, so I'll call it volts. We can just as easily do this with a current. The unit would be in amps, of course. Okay, so this is the general form that we use to then go plot each of these. And I can do this for the blue waveform, I can do it for the red waveform. All I have to do is change these 3 values to match what we see in the plot. Okay, so we're going to take this form, and we're going to go through what's called the phasor transformation. I'm gonna convince you that this is okay in the next video, but what we're interested in is representing this as a complex number, and we're going to do that with something called the phasor transform. We will take this time domain function and we will represent it differently, and we will represent it as what we call a phasor. Okay, we take the amplitude, and in polar form we say we have an amplitude at an angle of theta. Okay, and that's going to be in volts because it keeps that unit. So why is this possible? How is this okay? And then more importantly, what happened to omega? I had 3 pieces of information here, but when I go through the phasor transform, I lose omega. So how am I going to cope with that? And we're going to dig into that. Let's see, what else could we do here? What else could we do here? I think this is a good start. Next video, I'm going to show you how we take a waveform that looks like this, represent it this way, and then graphically make an argument for the fact that these are equivalent, and we can do math on this one instead of having to deal with the time domain function like that. Okay, this is where we're headed. Get ready for some animations, because I like doing this with some animations and I think it will help. Stay tuned and good luck, folks.